Okay, so let's go ahead. Okay, so this time I'm going to do things a little differently. I'm not going to give up until 7:30, so 2 minutes and 30 seconds. I'll give you guys up until, I'll give you another 30 seconds. So I'll give you guys until 7 minutes are left on the timer. So I'll be back. Sure, I can do a couple more summation. For the most part, we covered most of them, but I'll do a couple. We did most of the variations, but I'll do a few. And let me just write this down in case it take a little longer and the timer runs out. Okay, so let me just go full screen. So when it comes to recurrence relations, the main thing that you're going to have to end up doing is first calculating the iterations. So this is where you can get the most points on the foundation exam. Typically, it's about 6 points they'll give you just for the 3 iterations. So what they mean for iterations, let's say, for example, you have a function, let's say factorial, right? So let's say f of 3. You're going to have a base case when you hit f of 1. So let me just write this. Base case is base case at f of 1, right? So we can say this is n. So let's say n equals 1. So you have a base case right here. So you can think of the iterations as, for example, inside of this function. So you can say in f of 3, we're going to have a call that's going to go down to f of 3 minus 1. And then you can have a +1 call here. It doesn't necessarily matter, but I'll just have the +1 here. Then now you're going to have another call. This is going to be f of 2, right? So we have f of 2. And now inside of the f of 2 call, you were still recursing down until we hit f of 1. So now we're going to have f of 2 minus 1 plus 1. And now we're going to be going down to 1. And then this is where we're just going to be returning the base case. So I know factorial, you're not necessarily doing addition, but I'm just showing you how the whole thought process works. You're going to be descending down recursive levels. So you can think of it kind of, instead of thinking as a function linearly like this, we're going f of 1, f of 2, f of 3. This is what the iterations are. You can think of it, if you look at it from a different way, you can just have f1. Think of it kind of like a linked list in a way. So f3, f2, f1. And then this is, you can say this is your null. This is your base case. So that's one way to think about what their iterations are. Now, it gets a little different when it comes to the recurrence relations that they are giving us here, because they're not as simple as a simple O of n calculation. So it's not, you're just going directly just +1 every time when you're at f of 2, and then once you hit f of 1, you just return 1. It's not as simple as that. So for recurrence relation like this, we're going to have to start off by defining what are the recursive steps we're going to take. So what I mean by that is, let's define this as a variable. So we can say that f of, or t of n minus 1 is equal to, and pretty much the whole process for this is you're going to follow the trend that the current function is going down. So what I mean by that is you're going to have, right in blue, everything that's going to stay the same. So f of t of n. And if you're going down by 1 in every recursive call, that means now what you're going to end up plugging in for this variable in the next call is going to be 1 less. So right here, we're going to end up recursing 1 less in the recursive call. But then since now, once we go into this recursive call, we're going to have an n minus 1. That means that this n is going to be shifted by 1 downwards, just as this one was right here. So we're essentially just following the same trend step by step. And we can do this for further iterations. So remember, we have 3 iterations. So t of n minus 2. Oh yeah, and I didn't write what stayed the same here. So let me just do that real quick in blue only. So this stays the same. Okay, let me just rewrite. So I'm going to write in blue what stays the same. And then in white, what doesn't stay the same. So this is the change, if you notice right here. And then I'll write the same thing right here. So we'll follow the trend. We're just going down by 1 plus. And now we're just going to go down by 1 on n again. So that means instead of n minus 1, now we're going to have n minus 2. So this is essentially the formula you can go through. So now what we can do is we've essentially defined what we're going to plug in at every step. So right here, we're going to plug in this for our initial recursive definition of T of n. So T of n has a recursive call to T of n minus 1. So we're just going to plug in what T of n minus 1 is equal to, meaning all this right here. Or actually, you're going to plug this part into it right here. So this is what's going to stay the same. And you're going to also have to account for the minus 1. That's as you go down the iteration. So I'll show you what I mean, because it's kind of difficult to see what I'm saying. So let's go back to the original definition. So T of n minus 1. Or let's actually plug in the first variable. So I'm going to plug in what we have here in red. So we're going to have 4t of n minus 2 plus 2 to the n minus 1. And then remember, this is one of the things that a lot of people mess up. They always forget, because right now, all we've done, we have the same exact expression. The only thing is we've just plugged in something for t of n minus 1. So we still have our 4 here, so we're good. We plugged in what t of n minus 1 is. So this is t of n minus 1 again. And now we have to remember this term that we have on the outside, because if we forget it, then our answer is going to be wrong. So now what we're going to do is we're just going to distribute. We're going to distribute. There we go. So it's going to become 16 t of n minus 2 plus 4 times 2 t of n minus 1 plus t of n. Okay, so now what we're going to do, we're just going to plug in for this variable right here, t of n minus 2, we're just going to plug it into here. So this is going to go away, and what we're going to end up having in here is what we have equivalent to t of n minus 2. So let's do that. Okay, so this is t of n minus 2, what I just added in right here. And now what's going to end up happening is we're going to have to account for what's on the outside of this right here. So we're just going to copy this over. And there we go. Now to simplify, we just have to distribute 16. So let's do that. Okay, there we go. So this looks like a lot, but there's some things that we can do right now to make our life simpler. So notice how we've done the iteration. So we've done, we did one iteration, now we've done the second one, or actually we've done the third iteration. So now from this point is where we're going to try to get something called the general form. So the general form is the trend you're trying to see as you go through the recursive steps. So we kind of realized what the general form kind of was, or we were kind of building it up to get to what we have right now by, notice how we took these steps, minus 1, minus 1, minus 1, minus 1, and then we progressed that. So minus 1, minus 1, minus 1, minus 1. So we've kind of been building the same, we're kind of been building the logic that we have to. But another thing is you also have to notice these coefficients at the start are getting bigger. So this is part of the general trend. So typically what your general trend is going to be, you can tell what it's going to be is by the coefficient at the front, then how the variable in here is changing, which this is typically going to be changing based on K. And really most things are going to be changing based on K for the most part. And also what ends up happening with the sum that you're going to be building as you go through the recursive steps. So if you notice down here, aside from the coefficient or the constant in front of the recursive call, right here, we also have this big block of a sum that we're building. And we can extract information and look at all these numbers and see how are they changing in relation to each other. But first, we have to do some algebra to change things up so we can clean it up and actually see a pattern. So if you notice, we're working with powers of 2s right here. But if you also notice, we also have powers of 2 right here, and right here. So you might not see this one right here, but remember, any number to the power of 0 is 0. So this is actually has a 1 in front of it. And what we can end up doing is putting it in terms of powers of 2, because 16 is a power of 2, 4 is a power of 2, 1 is a power of 2. So let's think about how things are changing right now. So we have 2 to the 4, this is 16, times 2 to the n minus 1, or minus 2, plus 4, which is 2 to the 2, times 2 to the n minus 1. And then we have plus 2 to the 0, which is 1, times 2 to the n. Okay, so I'm going to ignore this right here, right now, but we'll get to it. So remember, there's a rule for when we have the same base and you have like exponents, like when you're multiplying. So if you remember, let's say you have a base b and one of them has a power x and you're multiplying it. You can think of it like this or think of it like this. And you have another number of base b to the power of y. So this can be anything, this can be anything as well. But the whole idea is that once you perform this multiplication, this is just going to be equal to b to the power of x plus y. So you add them together. So what we can end up doing is performing this operation on these terms right here. So let's apply that. So we can say this right here is going to become 2 to the n minus 2 plus 4. This right here is going to become 2 to the n minus 1 plus 2. And this right here is going to become 2 to the n plus 0, which it just stays as n, but I'll leave it there so you guys can see it. So now let's just do the algebra. So 2 to the n plus 2 plus 2 to the n plus 1 plus 2 to the n. So now we can see that there's something clearly happening right here. So we can see that something's clearly happening right there. Another thing we can also notice is that there's a common term. We might not be able to see it right now, but there is a common term across all of these. So the common term is 2 to the n. So you might think like, okay, how am I going to pull it out? So the same way that we join these powers, like these bases of the same powers together through like the rule that I mentioned, you can undo it as well. So like I said, you can go both ways. So this can go really either way. It doesn't matter which way you do it. You can go from this format to this format and this format to this format. So let's just do that so we can manipulate things to see if we can pull something out. So this right here, we can change it to 2 to the 2 times 2 to the n plus 2 to the 1 times 2 to the n plus 2 to the 0 times 2 to the n, right? So the common term out of all of this is 2 to the n. So we can rewrite this right here as 2 to the n times And what this is going to be times is just all of these variables right here, or all these values right here. So we have 2 to the 0 plus 2 to the 1 plus 2 to the 2. And yeah, you can just reconstruct if you just distribute. Okay, so it looks like a lot. I'm going slow and I'm breaking it down so you guys can understand every step. So as of right now, what we see is that we have a common term, 2 to the n, and we're building this summation out. So notice how it's going 2 to the 0, 2 to the 1, 2 to the 2. And now this is where we're going to start to incorporate these terms right here so we can see a trend. So now I'm going to bring all this stuff. It seems like we forgot about it, but it's going to come back just now. So we have 64 and t of n minus 3 plus this right here. So I'm just going to leave this in this form right now, and we'll go back to it. But let's see how things have been changing in this part of the equation right here. So if we just go all the way back to the start, because this is also part of noticing the general form eventually, is we see that we started with 4. So we start with 4 and then 1. So this value was 4, this value was 1. Then we ended up with this value as 16 and 2. So let's just write this down real quick. So we started with 4, 1. Then we start off with 16, and what was it? It was 2? Yeah, 2. And then we went to 64, and then this is 3. So let's think about how we can, since we're multiplying, let's see how it's changing. So we can do, for example, 4 to the 1 is equal to 4. So that gives us our first 4. 4 to the 2, let me just line it up, equals our first coefficient 4. Now, in the second iteration, 4 to the 2 is equal to 16. In the third iteration, 4 to the 3 is equal to 64. So this is how the term is changing. So for every single recursive call we do, or every recursive iteration we do, this value is changing by 1. And what is actually changing this value is whatever this is right here. So this would be the k. I know that it always comes up, the letter k, when it comes to recurrence relations. These numbers are indicating the value of k, because notice when it's 3, it's going to be 4 to the 3, and this is your coefficient. So now is when we've broken things down into a digestible way and we can see the trend. So I'm just going to start. I like to write GF for general form. And now we can start to build the answer. One quick thing, you have to remember your base case. So t of 0 equals 1. So let me just rewrite that down here. So t of 0 equals 1. And now right here, we're going to write up the general form. So we know that every single step, we're going 4 to the k. Then we're going t of n minus k plus 2 to the n. And we can try to see how the trend relates to this summation right here. So notice how for every iteration, so right here at the third iteration, we went from 0, so we can think of this as k. We went to 1, k again, and then this is going to be another k right here. So our k has been constantly changing. And notice how when we're at 3 for k, this summation only goes up to 2. So what that means is this summation is actually going to be running based off of whatever k is. So this is going to go up until k minus 1. So like I said, when k is 3, the summation goes from 0 to 2. And if we actually end up going back up to when, I think it was right here. Yeah, so right here, when we had up to 2, this is actually going up until k is 1. So this right here would be when this would be your 2 to the 0. And then if you end up solving this out, this term right here would end up being your 2 to the 1. So now you're seeing as k changes, this summation is also changing. So it's bounded by k. So right here. And of course, it's going to be 2 to the k because, you know, that's what it's changing based off of. or sorry, 2 to the I, 2 to the I, to the iteration. Okay, so this looks okay, but there's one little thing that we can do right before we actually start solving for, the final answer. So we have a lot of powers of 2. We have a lot of powers of 2. And one thing we can do is rewrite what we have here for 4k. So we can rewrite this a little differently. So we can think of this kind of as 2 to the power of 2 to the k. So this might look weird, but I'll explain. We know that 2 to the 2 is equal to 4, right? So what we can end up doing is pulling out the power of 2 and just have it up here. So that way we can have things in terms of like powers of 2. Okay. I don't know what that is actually. Let me remove that. Okay. So now we're going to go to solving the actual problem. So what you're going to end up doing, you're going to end up taking what's in here and setting it equal to what is inside of here. So n minus k is equal to 0. N minus k is equal to 0. So n equals 0. So right here, we're just going to plug things in for this general form. So now we know that n equals k, k equals n. And what we're trying to do is remove the reliance of this general form on k, because k is like a term you don't really know. You just want to put everything in terms of n if you can. So that's like your ultimate goal with this right here. So let's put this 2 to the power of 2 to the n. This right here is just going to end up equaling 1 because we set this equal to 0 and t of 0 is equal to 1. So we set this equal to 1 plus 2 to the n. And now, like I said, we're trying to remove all of the k's. Let's just plug in n for k. So now this is actually going to become n minus 1 summation of 2 to the I. Okay, so now we made some progress. And from this point on, we can solve this summation. So there's a formula for this. So I'll write it out right here. So you have a summation of, let's say, n I equals 0, and it's a base x to the power of I. This is just going to be equal to, and by the way, n is not the n in this function, it's just whatever's at the top. So it's going to be equal to x to the power of n plus 1 minus 1 all over x minus 1. So what we can end up doing is just plugging this in. So 2n times, and then right here we will have 2. Oh, you guys are asking some questions. Does it matter if we try to start the problem before you begin, or we can follow along? You can do it however you want. You can start it before, during the time. I don't know how many people actually do, but I hope you guys do, so you guys can like try to see if what you were doing was right. And yeah, you're giving the formulas. This formula, though, it's not on the test on every problem. There's some problems they'll give it to you, but this is like really useful to know. Like there's so many times that I'll use it when they don't even give it to you. And it's actually, from what I've seen, it's not even on the formula sheet. It's just in some problems they'll give you this formula. So definitely write this formula down, commit it to memory. It's very useful. And yeah, it'll save you a lot of times. Okay, so let's keep going. So x, this is x. Plug in n, so this is n. N minus 1 plus 1, right? Then minus 1. And think about it, if we do 2, so x minus 1, there's going to be all over 1, so we don't have to write it. So let me just erase this as well. And we still have this term out here. It's going to have 2 to the n plus 2n. That's going to be 2n minus 1. And now we can finally do is just distribute it. You can probably just leave it in this format, but distributing it also works. So just do it real quick. Times 2 to the n. So we're just going to do n plus n. then minus 2 to the n. And notice we have 2 of the same term right here. So you can say that this is 2. So this is going to look really weird right here. So you can say that this is just like 2 of the same term. So like 2 times 2 to the 1, right? Because remember, if you add something twice, it's just equal to that number times 2. So this, we have 2 of these terms. So that's 2 of the 2 to the 1, right? And we can multiply these terms by 2. Minus 2 to the n. And again, we can use the rule of exponent when you're multiplying. So this is going to end up base b times x plus y. So we're going to have 2 to the n plus 1 minus 2 to the n. Okay, so that was really long. I was going very short or very slow so you guys can understand the whole process. But this is the final answer you end up with. They might have it a little bit differently because, you know, sometimes they simplify things more, sometimes they do it less. So it might be a little different, but let's see what they ended up getting. Okay, so let me zoom in. So somebody asked real quick before I go over the answer, what would we put if they ask in terms of an O bound, a big O bound? So right here, if you notice, we can remove all sorts of constant. So you could put this right here in terms of 2 to the n, because you can remove this constant right here. Then that would leave you with 2 to the n minus 2 to the n. But again, this would just be 2 to the n times 2 to the n right here. And again, okay, then let me just do this real quick. So ultimately, it's not going to be like you're going n squared. It's just going to be 2 of the same factor. So overall, the function would just end up being just 2 to the n in terms of big O. Yeah. So you can like manipulate it around, remove some constants and stuff. So that's how you can get your big O bound. But yeah, let's get back to this right here. So let's see what they ended up doing. They did the iterations. They ended up building out this summation right here, the same exact way. And then they realized, okay, there's a common term, 2 to the n. And from there, yeah, this was the general form. So let's see how our general form paired up. It looks like theirs is slightly different, but I'll explain why it's different. Okay, so they had 4k t of n minus 1 plus 2n, and then k minus 1, I equals 0, 2 to the I, 2 to the n plus I. Okay, so this is the same exact thing right here. And let me just explain why. Remember when you have a summation, let's say you have a constant term, let's say you have 5i, let's say this is going n and this is going from 0. This right here is equivalent to 5. You can just bring the constant out. So this right here can be just I, and I equals 0. So this is the same exact thing. What they ended up doing, they just kept this 2 to the n inside. Since this is going to be multiplied by the entire summation, so you can have like 2 to the n times 2 to the n plus 0 plus 1. They just ended up including this in each term. So they pretty much didn't pull out the 2 to the n. The reason you can pull out the 2 to the n is because if you think about it, whenever you call a function, the n is always constant. It's never going to change, because then, you know, you're going to have like infinite while loop. Like every time you call a function, you pass a finite value. Okay, 3. And then now you're going to end up having some sort of base case you end up hitting, right? So that's the whole idea behind what they did. If you just put this into the summation, you end up with this right here. But yeah, you can just pull that out. Really what it ends up looking like is the same rule that I mentioned, which is this right here. So that's what they ended up doing right there. And as for the rest, yeah, they ended up pulling out the 2 to the n right here at the end. So that's what I meant. And yeah, they ended up with the same exact formula. So notice how what I mentioned, they don't give you the formula anywhere, but look at the same formula that I used right here. Same exact thing. So they don't give it to you, but they expect you to know it. So definitely write it down. And yeah, you end up with the same exact thing, pretty much. So that was that question. So anyone have any questions on that? I know it was long, but just wanted to cover all the bases to make sure everyone understood that.
Could you keep that screen there real quick?
Sure. I can go back to it later, but I'm gonna move on to the next question now. Okay, so let's go on to the next question. Okay, so I'll come back at around 7 minutes on the timer. So what is a closed form solution to the following recurrence relation? Show all of your work and provide final answer in big O notation. So base case and the initial recursive function. So let's start on it. So we have T of 1 equals 1, and then we have T of n equals 1. Okay. So we have the same exact steps we're going to have to end up doing. So we can define the variables. So let's do that real quick. So we have T of n divided by 4. So notice, let's say you have an array, right? So you have an array of 4 items. So if you're going to divide n divided by 4, so 4 divided by 4, that means you're kind of going to be dividing into 4 different sections in a way. Like you're going to like split, or actually not necessarily that. You're going to be going on a fourth of the array. So you're going to divide whatever n is by 4. You're going to do that recursively. So pretty much what I'm trying to say is the trend is you're going to go n divided by 4, n divided by 16. So this is what our recursive steps are going to look like. And if you think about it, a common example we know is merge sort. You divide the array into 2 parts. So for example, you do this subsection, then this subsection, etc. So you do the same process. So the same trend is going to end up happening, but it's just going to be a factor of 4 in this case. So that means that this is going to be equal to, and I'm right in blue, what stays the same again. And what changes is this. It's now going to be 16. So we're just going to stick to 4, right? We're just going to stick to power of 4. We don't know anything else as of right now. We can't see it right now, but maybe later we can see something else past, base powers of 2 or simple powers of 2. So again, in blue, everything is going to stay the same. Okay, plus 1. And this right here is going to be 64. 16 times 4 is 64. Okay. And we can go another iteration, but I think you guys will be able to see the whole idea, not having to do it again. But sure, you do 2 or 3 iterations on the exam. You have to. And I believe this right here just counts as 3, if I recall correctly, because in the other example, they only went up until 3. So this right here would be good. So we already know what to do. Just got to plug this in for this right here. So let's do that. So 2 times, we're going to plug in the variable of T of n minus O divided by 4. So over 16 plus 1. And remember, don't forget, the plus 1 on the outside. So let's distribute. Okay, so now we're going to plug in this right here in there. Let's do that. So I'm just doing the math right now. So we're just distributing stuff over. Also, notice how I'm not combining these numbers. You could, but I think it's easier to just leave them because I'm sure you guys can see what's happening right here. And you know what? Why not? Let's go one step further. I know we don't have to, but let's just go one step further. So I'm not gonna write it down here for 64, so you guys can just get some practice doing it on the fly. So let's just write our final. So we have this right here. Let's also have this right here. So these are our steps, and we start off right here. Let's go one more. 64 times 2 is 128. Plus 1. Remember, summation at the end. Okay, so this is the final one I'm going to do. Oh, yeah. Sorry, my bad. It's we're doing times 4. Good catch. Okay. All right, so for this type of problem, it might be kind of hard to see how everything relates to each other, but there's going to be, like, I guess you can say a trick or something you can realize. Let's think about first you have to find what your K might be, because right now we have like an 8, we have a 64, we also have a 4, we also have a 16, so that might kind of give it away. But let's think of it like this. So right now we're at 16, right? So let's try to put this in terms of a common power. So let's just try out 2. Even though it seems like this right here is changing based on 4, which it is, but let's just think of this in terms of power of 2. Actually, first, let's do power of 4, right? So 16, 4 squared. Another way you can think of this in powers of 2 is 2 to the 2, which is 4, and then you square that, which will give you 4 squared, 16. So again, this is just, you multiply these exponents when you have an exponent raised to another exponent. So this is just 2 to the 4, right? So for this right here, we just have 2 to the 4. And this value right here, let's try to see what this is. So how can we get this in terms of power of 4? So this right here is just 4 to the 4. Well, let's write that in terms of powers of 2. So 2 to the 2 to the 4, which is just 2 to the 8. Right? Okay, so this is where we're at right now. 2 to the 8. Okay, so we notice how at most iterations, this is how these things are changing. So let me just write this right here real quick. So this is 2 to the 3. 64 is 2 to the 6. And let's go one step further up until this one. We don't have to go on this one. You guys will see what's happening, but this is 2 to the 2. This is 16 is 2 to the 4. So I'm sure you guys are noticing there's something happening right here, which is this term in here. It's growing like not necessarily twice as fast, but it's squared. So it's squared in terms of like the correlation between these two values. So what I mean by that is, how can you get from 2 to the 3 to 2 to the 6 easily? Well, you can just square this value. An exponent raised to an exponent gives you like the multiplication of the exponents. and that's how we can end up getting the same value. So what we notice is, let's just write down, so GT, we're going to go, or sorry, GF, I'm going to go into general form. So I'm going to write down this part right here. Let's do that in blue. So we can say that, oh yeah, and by the way, let me just write this right here. You can think of 2 to the 6 as 2, like I said, times 2 to the 3. And again, you can get that by squaring it, but let's just think of it like this right now. So this is just 2 times 2 to the 2. Or sorry, this term right here is 2 to the 4 times 2. There we go. So we can think of this as 2 to the power of k, right? Because notice how this value right here, it's always getting multiplied times 2. So it's always getting multiplied times 2, but what's always stays, what's the thing that's changing is this value right here. So notice this is a 4. I know it's really small, but this is a 4, this is a 3. And if we go up here, this value is 2 times 2 to the 2. And that goes from 2 to 2 times 2 by multiplying times 2. So the whole thing that I'm saying is this is your k. So whatever this value right here is your k. And the way the trend is changing is you're going to have n over 2 times 2 to the k. So I hope that right there makes some sense. So we're multiplying whatever we end up getting from right here, like the exponent, times 2, and that's how we end up with the value that's down here. Okay, so now this portion of the equation is done. We've already got that down, but we still have the summation towards the end. So again, you can see that there's a clear trend, right? So let's just think about it in reverse. We go from 1 to 2 to 4 to 8, right? So let's think about this sequence a little differently. Let's order it. Let's put it in order. So 1 plus 2 plus 4 plus 8, right? And now let's think of this in powers of 2, which is, it seems like the rest of the equation is going based off of powers of 2 in a way. So let's think of this in powers of 2. So this is 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. Okay, so we notice that the final number, or the final power of 2 that we're going to be adding in the summation is 3. And we also notice that the 2 to the k is currently 4. So k is currently 4. So similar to the previous problem is that this value is going to be 1 less than k every time, like as we go through the recursive call. So this entire value is going to be equal, or the final value that you're going to add is a power of 2 to the power of k minus 1. So let me just rewrite that a little differently. So it's going to be equal to k minus 1, I equals 0, and it's going to be 2 to the I. So like I said, k is 4, and we're only going up until 3. Remember, the summations are inclusive, so we're going from 0 up until k minus 1, including that value. So the final value would actually end up being 2 to the k minus 1. And if k equals 4, that means that 2 to the k minus 1 is 2 to the 3, which is what we have right here. Okay, so far so good. So this looks really weird. I know there's not really that many questions that have this right here, but let's go back up to the base case. So now that we found what seems to be our general form, and we checked it out, we checked that how the values are changing and all that stuff. Now let's go into this base case. And again, if you have a base case, t of 1, and then you just set it equal to what you currently have in your general form. And what I mean by that is you set what's inside equal. So let's set 1 equal to n divided by 2 to the k. And now from here, we can do some algebra and get this to the other side. Equals n. Okay. So now this is where something kind of strange is going to happen, but it's, again, part of exponent rules. So let's say there's going to be a little bit of a different rule, but let's say you have a base b and you have it raised to the power of x, like I said before, and I've done this a million times so far, but if you raise it to the power, it's just going to be equal to b times x minus times y. So right now, what we can end up doing is solving for a common term that's throughout all of our general form right here, which is 2 to the k. So we can end up doing that by rewriting this a little bit differently. So we have 2 times k, 2 to the k, and then now we square this. So like I said, x times y, k times 2 is 2k. So that's just 2 to the power of 2k. So that's what we're working with right now. And now we have this equal to n. So how can we solve for n? We just take the square root, so we can remove this square. So that means now we're going to have square root of n. So we have 2 to the k is equal to square root of n. Okay, so we made some progress. Now we have 2 to the k. Now from this point, we're going to go back to our general form, and we're going to try to plug in things where we can. So let me just pull this down so we don't have to keep going back up. Okay. So this is general form. So we have 2 to the k. So let's plug that in. We have a 2 to the k here. We have something that kind of looks like a 2 to the k right here, but I'll show you what you can do with this right here. So 2 to the k, let's plug in square root of n, right? Because we know that at this point, they are equivalent. So we can just plug that in. Now we have this value right here. For this right here, let's do a little bit more of solving so we can remove it. So we have t of n over, and now let's do something with what's down here. So we have 2 to the power of 2 to the k, and we know that 2 to the power of 2 to the k is equal to n. So we could literally just plug in n. So let me just put this in parentheses so you guys can see it a little differently. So if we have t of n over n, and let me just write this out real quick. So t of n over n divided by n is just 1. So we have t of 1. And if we remember our base case, t of 1 is equal to 1. So since we're going to end up with t of 1, we could just end up saying this is just equal to 1 right here. So let me just copy this over. So this right here is just t of 1, which is 1. And we can just remove that 1, right? Okay, and now we have to solve this summation. And this is where the same rule comes back into play. But first, let's take note of something real quick. Let me see. Actually, never mind. So we have this going up until k. So remember, our whole goal of this, of what we're doing here, is we're trying to remove k from the equation. So at some point, we're going to have to end up solving for k, so we can end up removing this summation out. But there's a trick that I want you guys to know real quick. Okay, right here. So whenever you have a power of 2 and you're going up until k minus 1, I know that the whole goal is to try to remove k. So typically what you end up doing is plugging in n right here, or whatever you end up getting, like equal to k. But if you think about it, if we set this equal to k, we're going to have some disgusting thing right here. So we're going to have something like horrible, like something like this. And we don't want to deal with this, right? So, because this is bad. So what I'm going to end up suggesting to you guys is instead of trying to get this and then plugging this into here and somehow trying to get it right, which you probably could, but I wouldn't. There's an easy formula for this right here where you're doing powers of 2, but you're going up until k minus 1. So the formula is literally just 2 to the n minus 1. But more realistically, what we ended up having was 2 to the k minus 1. So let me just rewrite that. Plus 2 to the k minus 1. So this is a formula for this right here. Because this way, or you can solve it with the common formula, you know, the formula that I told you guys about. So the formula again is this right here. So we can use that as well, and we'll end up with the same answer right here. So you can just plug it in, get the same thing. And it's important that we kept the k here because, like I said, if not, you're going to have something disgusting like this to deal with, or the log square root of n to deal with. But since we have something for 2 to the k, 2 to the k is equal to square root of n, we can just end up plugging that in, and that'll remove our dependency on k. We want to get everything in terms of n eventually. So now we have 2 to the n plus, remember 2 to the k is equal to square root of n, okay, I just do minus 1. So you think about it, this is just 2 square root of n minus 1. And we're trying to find the big O. So obviously drop all the constants, throw this out, throw this out. So our big O is square root of n. So does anyone have any questions on how I got here? Okay, all right, so let's check the answer. Okay. Oh, Tyler just asked a question. Let me explain it real quick before we go back. So he said when you plugged it into the formula, where's the 2x minus 1 in the denominator? Okay, so okay. I see what you're asking. My bad. I did not mean this as a 2. I meant this as an x. My bad. I wrote it incorrectly by accident. There we go. So this x minus 1, if you think about it, 2 minus 1 is 1. Anything over 1 is just whatever's here. So that's why you don't have to write it. Let me just plug it in real quick so you can see it. X k minus 1 plus 1 minus 1. Like I said, this just ends up 2 minus 1 over 1. It'll just be this term itself. So this just ends up being 2 to the k minus 1. And that's how I ended up getting that. So let's go to the answer real quick. Okay, yeah, so they did it a little differently. What they ended up doing, let's just analyze what they did. Instead of plugging in n right here, they ended up plugging in 4k. And again, if you think about it, we ended up getting to 2 to the power of 2k. This is just equal to 2 to the power of 4k. So instead of plugging in for this value right here, they just pretty much plugged this in for n right here. But again, it's the same value over the same value. It doesn't matter if it's n, doesn't matter if it's 2, doesn't matter if it's a million over a million. It'll just end up being 1. So they end up with the same thing. So, you know, there's different ways to go about these things. But generally, I like to keep it the same way. I want to like plug in at the bottom. That's just how I've always done it. So yeah, that's the whole idea. But we ended up with the same exact thing. So that's that. Let's go on to the next question. Okay, so I'll give you guys until 7 again. Oh, and also, anytime they give you this stuff, you know you're going to use it. If you see it, you're on the right track. So this O of n, I'm not going to keep it as O of n. I'm just going to keep it as n. And yeah, base case. So let's start. Oh yeah, and also let me just write this in case we don't finish in time. Okay, so this is the same iteration. So now I'm not going to write down T of n minus 1 equals and then plug it back in. I'm just going to go straight through it because I'm sure you guys got it now. So let's just go straight through it. So like I said, constant always stays the same. T n divided by, if we have a 3 at the start, let's just keep going with 3, but let's increase it. So if we're dividing 3 and then we divide a subsection of 3 into another 3 parts, then we're going to go to 9. So plus, and remember, we have this n right here, but a lot of times what ends up happening is you're going to end up cycling stuff down. So what I mean is what's here, what was used to be in here is going to end up probably going in here for wherever the other n is. And then eventually what's going to end up here is going to end up following the same pattern. So you could just draw these lines out, but let's get through it. Remember the n on the side. So that's kind of the summation thing you're building. Okay, so I'm going to keep going. So 9 times 3, 27 plus, and now we're going to want to keep going with the trend. So if we were dividing previously by 3, now we're going to divide by, like I said, 9. It's going to be n divided by 9. And now we're going to keep going with the summation. Just n. Distribute everything over. Okay, so we've done 3 iterations right now. So let's rewrite what we've got right now, okay? So let me just rewrite. These are going to be like the solved steps, I guess you can say. And this final one as well. Right? So let's see if we can see what's happening. First, let's rewrite the summation. So I'm just going to focus on that right now for this part. So plus, and we can see that in every single one of these values, we have an n. So what we can do is pull out the n. And now what I like to do is put things in order. So in sorted order. So it's easier to see, I guess. So this right here, even though there's nothing, it's a 1 over 1, right? 1 is always there. So we have 1 over 1 plus 2 over 3 plus 4 over 9. So I'm sure you guys already see it. Times 2, times 2, times 3, times 3. Okay, so now we see what's going on. And now we just have to think about how we can write it in terms of a summation. But first things first, we have to kind of realize what our k is. Wait, what happened? It's supposed to be 8. Oh, did I end up doing? I plugged in a 4 by accident. Right. Yeah. Good catch. My bad. Okay. Yeah, guys, I make mistakes too. So just tell me so I don't keep going down a path. Yeah, I'll make some mistakes like that sometimes. So let me just put the 2. There we go. So now at this point, let's see how this is changing. So let's do a summation because we know we're doing a summation of something. So let's just set it up. So we know that we're multiplying times 2, and we're also dividing by 3 every time. So if we're multiplying times 2 and dividing by 3, we're going to have something that looks just like this, right? And I'm not going to put the top bound just yet, but we will get to that. So let's go and try to find our k. So we notice this right here, we start off with 2, then 2 times 2, then we did a value that is a power of 2. You can eventually get it by multiplying 2 times 2. It's 4. Then 8 you can also get through 2s. So let's just put this in terms of 2s. Right? And this, we can put it in terms of 3s. So this is just 3 to the 3. And let's just go back to these red dots and just see if we can, find anything. So this is just 2 to the 2. This is 3 to the 2. And same thing up here. Let's do it one last time. 2 to the 1, 3 to the 1. Okay, so we can see clearly that at every given iteration, these values are changing by 1, like together at once. Right? So maybe that can help us realize what our k is. So I'm sure you guys can kind of tell what it might be. So our k is actually 3. So if our k is 3, let's think about how many times we end up doing the multiplication. So this right here, let's just rewrite the summation a little bit. So for explanation, so this is 2 to the 3 to the power of 0 plus 2 to the 3 to the power of 1 plus 2 to the 3 to the power of 2. So let's again take note of what the summation ended up like at the final term in the sequence once we like sorted it. And or actually it's not really like in sort order, but you guys kind of see what I mean. I mean, like it's as we go through the multiplications, what I meant. Okay, so we ended up at 2, and notice how our k, it ended up at 2 for a k of 3. And right here, it ended up at 1 for a k of 2. And here it ended up at a k of 1 at 0. So this is 1 over 1. So this is just bounded by k minus 1. So this right here is just going to be k minus 1. Okay, but there's going to be one thing we're going to have to end up actually changing on this, but let's keep going with what we had here. So what I'm doing right here is just calculating the general form, but I did it like in different steps, just bringing in different elements to create it. So this is just 2 to the k, and then t of n divided by 3 to the k. Okay. So there's one thing, I don't know really how to explain this otherwise through, I guess, calc, but for those that have taken the calc, like certain geometric sequences, whenever this value, so you have something in the format of like geometric sum, whenever you have something where it's like a summation where, let me write this like this, a times r to the power of n. So you have something like this where a can be anything, right? But let's say your r value is less than 1. So you take the absolute value of the r value, it's less than 1. Then you can kind of say like this is, you can put this to infinity because this is a very common pattern. For those that know calc, this is going to, the value is going to end up like approaching, 0. It's going to end up approaching 0. So that's like the whole idea behind this, because if you notice, 2 to the power of n, 3 to the power of n, as n grows, so like I know this isn't calc, but it's relevant to kind of like CS stuff, but as n grows, this value is going to end up approaching 0, because let's say you do 2 to the 100 over 3 to the 100, this value is going to be way bigger than what is up here. So it's going to end up approaching 0 eventually. So there's a summation formula for this. So you can just put this to bounded by infinity. And there's a formula on the foundation exam formula sheet, where essentially what you're going to do is set this right here. This is your A. So your A is just any value, but this really is just 1. You have a 1 just sitting out here. And then this right here is your R value. So let's just think of it like this. So this is going to be a 1. So really the formula is just going to end up being, let's just say answer. I don't know what else this right here would be called, but you can just set this equal to A over 1 minus R. This is the whole formula. And A in these type of problems is always going to be 1. So you can just think of it as 1 minus 1, or 1 over 1 minus R. So let's plug in the R. The R is 2/3. So 2/3, it's going to end up being 1 minus 2/3. That's going to give you 1 over 1/3. And if you do some algebra, this is just 3 when you flip the fraction. Okay, so I know we dipped into calc, but this just ends up being 3. But I'm just explaining how you end up getting like what they had in their in the formula that they gave you. So remember, they gave us, so we didn't need any calc. I'm just explaining that. So this right here was going to be equal to 3. So that's how they ended up deriving that. So there we go. So we can just plug in 3 for this right here. So this is just 3n. So now we still have our general form. And now is when we're going to actually start doing stuff with the general form. So at this point, our general form, let's just see what our base case was. T of 1 equals 1. So set the values inside of the t's equal to each other. So we're just going to have 1 equals n over 3 to the k, which is going to end up giving us, okay, that's not an n, that's a 2. N over 3 to the k. So that's going to be 3 to the k equals n. Now, log rules is take log. Whatever the base is, set that down here. Whatever is right here, set that right here. And whatever the exponent is, set that outside. So k equals log of 3 to the n. So that's what we have right now. Okay, and now we're going to end up doing is plugging in k wherever we have a place to plug in k. So let's just see in this function, where can we plug in k? So let's plug in k right here. So we're going to have 2 to the power of log 3 to the n. And again, this just ends up going to 1. So this is times 1. We can remove it. Plus, and then we're going to have 3 to the n. Okay, so now at this point, we have the equality that they gave us. So this right here, so log 2 to the log of 3n is just equal to n log of 3 to the, this was actually a 2 on what they gave us. I just wrote it wrong. So n to the log base 3 of 2. So let's rewrite this. Is going to be n to the log base 3 of 2 plus 3 to the n. Okay, so now at this point, we're going to want to see, remember, when we try to find a final answer, we're going to want to see which of these terms is bigger. And we're going to be growing based off n. So if we think about it, n is really just n to the 1. So you can just write a little 1 here. And now you might be like, okay, how am I going to compare this right here? So there's a simple rule. If you know how to use an exponent and log, it's easy to solve this, but let's just do this for now. Let's set these values in kind of an inequality. So, but first, let me show you guys one thing. So we know that 3 to the 2 is equal to 9, right? We know that 3 to the 1 is equal to 3. So if we put this into a different format, so we put this kind of into like log format, we can say that log base 3 of 9 is equal to 2. Log base 3 of 3 is equal to 1. Okay. So what I'm trying to show you guys here is we know that at least log base 3 of 3 is equal to 1. Okay. But the whole idea is if this value is less than 3, we know that it's going to be less than 1. So log base 3 of 2 is going to be something less than 1. So this value is going to end up being less than 1. And if this is less than 1, you can think of it kind of like this. You can just plug in your n right here. And that'll tell you which of the two is a dominating term. So I hope that makes sense. I just made like a quick little inequality showing you guys how it works. So as this value right here ends up going down and decreasing, like exponentially, you end up seeing that the exponent value is going to end up going down, down, down. So if we go less than 3 and log base 3 of 3 equals 1, if we go less than 3, that means that this value is something like who knows what it is, but it's less than 1. And that's all we care about. So that means that the overall like big O runtime is just going to be O of n for this one. So I hope that right there made sense. So let's go to the, okay, I don't know which one it was. I think it was this one. No, it was not this. It's this one. There we go. So I ended up with the same idea. We will take the bound of the summation to infinity instead of taking fk to the -1. So again, they did that for like calc reasons. You don't really have to know why, but it pretty much approaches a value. It converges, the whole idea. It ends up approaching a value, and then that value just happened to be 3. So it's like it's finite over time. And like I said, they ended up comparing which is the dominating term. So the same logic, you can just put an n under this, both of these, and you end up seeing which is the dominating term, and the answer is O of n. So that's that. So let's do one more of these, and then we can move on. So this one should be quick. I'll actually just start on it right now so you guys can see it, and we can move on quick. Okay, so T of n equals 2T of n divided by 2 plus 1 for all n greater than 1. Okay, so, oh yeah, in base case as well. The recordings are on the SHPE UCF YouTube channel. So you go to this website, passivefoundationexam.versal.app, go to this link, and it'll take you to all the videos. I'll be uploading this probably tomorrow. So yeah, okay, let's go on to this question. So again, I'm just gonna go fly through it, Let's just go ahead. Plus 1. Then we're going to end up the summation at the end, plus 1. It's going to be equal to 4 T of n divided by 4. Let's distribute the 2 plus 1. And let's keep on going. So 4 of 2T of n divided by 8 plus 1. Remember the summation. So I'm going to say that for every single iteration I do, remember the summation, because if you forget the summation, then good luck getting the question right. So here we go. Then we distribute the 4. Remember the summation. Okay. And all right. So this is good enough. We don't have to keep going from here. So we notice there's a summation. So I've said it like a million times, but let's just box it up and let's leave it right there. Let's see how these values here are changing. So we noticed that we started with a 2, and then we went to 4, and then we went to 8. So we can probably use base 2, and 8 is 2 to the 3. 8 is also 2 to the 3. And let's see the summation. So we can write it like this. So a summation, if in each recursive call we're going k is 3, then, and we're going up until 4, remember 4 is 2 to the 2. So how can we get from 2 to the 3 to 2 to the 2? We can do -1. So we can say this is your k, so k minus 1. So this is how the summation is changing. So it's a k minus 1 bounded. So typically, a lot of times you're going to see k minus 1. K minus 1 equals 0. It's going to be 2 to the I. And again, you can tell by, rewriting it in powers of 2. I won't do that, but I'm sure you guys can see that right here, the powers of 2. So I'll just write it right here. Okay, so finding our GF right here, general form. So this can be 2 to the k, and we have t of n over 2 to the k. Okay, so now we have our general form. Let's use our base case, t of 1 equals 1. Set what's in the base case, and what you pass into the function, equal to what's in this one right here. So we're just going to have 1 equals n over 2 to the k. And this is going to give us 2 to the k equals n. And if we rewrite this just to get in terms of k, you never know, it'll probably help. Log base 2 to the n. So easy way to do this, 2 to the k gives you n. So you can just do this cycle thing. Okay, so now let's plug in. Let's try to remove as many k's as we can in one go. So this is n, right? Plug that in, 2 to the k equals n, so plug in n. Then we're going to have t of n over n, because we plugged in 2 to the k. We know that this is really t of 1, and we know that t of 1 is equal to 1. So we can just remove this whole thing right here. This is times 1, and we can remove the times 1. So we're going to have n plus. Now from here, we're going to have this summation thing, right? And let's see what we can end up getting from here. So remember the formula. The formula is everything. This formula is so useful. So I'm just going to plug it in, I'm not going to rewrite it, but I'll just plug it in. Okay. Oh, not x, sorry. Your x is 2 in this case. This is your x. 2 to the k minus 1 plus 1. Then you have minus 1 on the outside over 2 minus 1, which is just 1, so we can remove that. So this is what we're left with. We know that minus 1 and plus 1 cancel out. So now we have n plus 2 to the k minus 1. So we're left with n plus 2 to the k minus 1, and we know that 2 to the k is n, so we have really n plus n minus 1, which is 2n minus 1, and this is the closed form, but if they ask us for the big O, we know it's just O of n. So let's check out the answer for that. Okay, so exactly that. So I hope that made sense. Yeah, if you guys just realize, if you just put everything's in terms of powers, because really all these sorts of things, they're just testing if you can see how the powers are changing, and also if you see like the pattern with the summation. So the summations are typically easy to see. Sure, there's some examples that are harder to see, but like I said, like it always comes up with experience. Yeah, this is one of the easier ones. This is definitely one of the easier ones. Like the other ones, um, honestly, even this one wasn't that bad, but it was just a little trickier, for sure. But like the whole thing where they just put it to infinity, they didn't really explain that, which they probably should, but they just kind of assumed that you know how to do that. But the whole idea is that as the value of n grows, then it's going to start approaching zero, meaning it ends up, for those that have taken calc, converging. So that's the whole reason they can set it equal to 3. But yeah, most of the other ones, like the square root of n, that one actually wasn't that bad. It was just tricky manipulating the numbers, and seeing how the numbers change is pretty much the whole key of recurrence relation when it comes to the foundation. But yeah, let's move on to the next section. Okay, so next section, I don't know what that was. Okay, so I'm gonna go for, I said base conversion first, but it's getting a little late, so let's do algo analysis first. So I'm just gonna hop into the question. Okay, so please zoom in a little more. Okay, so an algorithm to process input data takes n cities, about n cities takes n factorial time, O of n factorial time. For n equals 10, the algorithm runs in 10 milliseconds. How many seconds, not milliseconds, seconds, should the algorithm take to run for an input size of 12? Put a box around your final answer. Okay. So whenever you see these type of timing questions, they're a lot easier than they seem. Most of the time, it just comes down to knowing this formula and, okay, runtime. So you guys have probably seen this as something else, but runtime. So when I say runtime here is n factorial. So that's what you would plug in for runtime. So typically, the way these questions come up is they give you a runtime with a number and say, okay, it runs this long for this input, how long for this input. That's pretty much what you're doing. So what the process typically follows is you plug in the numbers. So you plug in the timing that they give you, and then the runtime, and you plug in n for like whatever. Let's say this is 10. You plug in 10 for whatever's in the runtime. You end up isolating C, so C equals something. So after you find your C, then you just use your new n, so your second n. So in this case, your second n would be 12. Then you have your, I guess you can call it your found C. So after you solve for C, then you have the runtime again. So this kind of looks kind of bad, but the whole idea is you're going to solve for C. Once you solve for C, use the C you found to find the amount of time it'll take for the same function runtime, but with a different value. So that's really the whole idea. So let's hop into it. So we know we're going to start off with n equals 10, and that runs at 10 ms. And it's saying how many seconds should the algorithm take for size n. So how much n equals 12 time. Okay, so let's start off. we're going to have 10 ms equals, and now we have c. We don't know what c is, so let's just plug in the runtime. So our runtime is n factorial. So if we plug in n equals 10, we're going to have 10 factorial. And now from here, we can end up doing is dividing it from both sides, the factorial. So now we're going to have, just divide it to this side. So we're going to have 10 ms over 10 factorial times, or equals c. And with just one quick thing to simplify this right here. We can simplify right here. We could also not, but let's just end up doing it right now. So we have 10 ms, right? And we have a factorial. So we know that factorial, it's literally just, let's say you have a value x factorial. You're going to have x times x minus 1 times x minus 2 until eventually you hit, whatever x is minus something, it'll end up stopping at 2, and then now you're going to end up at 1. So 1 is always the base case, or 0. It's also equal to 1. But let's just stop at 1. So this is essentially how it works. So we can break this down and think of it as 10 factorial times 9 factorial. So what we can do with that information right now is okay, let's just erase this. Set this equal to c again. And we have a 10 and a 10. We can remove this 10. So now we have 1 over 9 factorial. So that's a small little thing we can do, but it may help it go through easier. It doesn't really matter. You can do it here. You cannot do it here, but I like to do it at this step. So now let's go into t of n equals 12. So now we have our c n factorial, and let's plug in the runtime. So we're going to have n factorial, n is 12. So we're going to have 12 factorial. So now right here, like I said, we can break it down. So if we think about it, 12 factorial is really 12 times 11 times 10 times n factorial. And n factorial can just be n factorial. You can just divide both of these out. So really, you're just going to be ended up with 12 times 10 times, or 12 times 11 times 10. Let's do this math real quick. This is just going to be 11 times 10, 110. And now we're going to have this times 12. So just do that real quick. So that's going to end up being 1. Okay, so 1320. So this right here is going to end up giving you 1320. And that's going to equal our runtime for T of 12. But one thing is, okay, let me see. They wanted to give you seconds. So if you had milliseconds and they want you to do it in seconds, you're going to have to multiply by 1,000. So to go from millisecond to second, you multiply by 1,000, and that'll give you like the final time. So I multiply by 1,000, and that'll give you the final runtime. So let's see the answer. Actually, sorry, I meant to divide, my bad. So you end up dividing by 1,000. Divide by 1,000. There we go. They give it to you in millisecond, they want you to go to seconds. So yeah, just divide by 1,000, that'll give you the runtime. There we go. That's the amount of time that it takes. So they followed the same step. So they ended up with 132 divide, and then from there you end up with this value right here. So that's about it. All right, so let's end up going on to the next question. Okay, so this is a big O. So this one shouldn't be that bad. So let's write this down. So I'm just going to do 1. Okay, so this is average and this is worst. So it's saying push operation onto a stack implemented with a linked list storing n elements. So they want us to give us the average case and worst case for this, but a lot of people ask me like, okay, how do you actually end up calculating these? How do you end up seeing like how much time it's going to end up taking? But really, to these type of questions, unless it's something simple like binary search tree or heap, where most of the time, or for example, ABL tree, it's all log n. On these type of questions, you're going to have to actually know how things are implemented. So sure, you can memorize them, but it goes farther to actually understand why the runtime is what it is. So push operation onto a stack with a linked list storing n elements. So typically the whole idea behind the stack with the linked list is, let's say you have nothing. So you end up creating an element. So this is now the top of the stack. And what you end up doing, if you want to add another element, you just create a node and then you just route it to this value right here. And if we want to do it again, still one last time, we create a node and set the next to the old top and set this to be new top. So all we're doing is mallocing a node, setting the next pointer, and then changing what the top is. So all of that is all of one operation. So based on how they teach you in the course to do this, the average and worst case is both all of one. That's just based on how they teach you. There's probably some bad implementation, but in the way that they teach you, it's all of one. Some bad implementation that might make it worse, but they're thinking about how it should be implemented. So printing out the permutation of 1, 2, 3, n. So it's one of those things that you can analyze the runtime of, but it'll take you some time to like really understand why it is. But the whole idea with permutations is just always like n factorial. So let's just write that in n factorial real quick. And the whole idea is, let's say you have 3 letters ABC, and let's say you want to permute it. So what that means is you're pretty much going to end up putting every value in another location, or it could be in the very same location. So let's say we have a sequence ABC. We want to find all permutations of ABC. So I'll just end up running through it myself so you guys can see, but you end up seeing the final answer. So you want to permute ABC. You're going to end up first with ABC, ACB. You're going to have BAC, BCA, and then finally going to end up with CAB, CBA. So this is meaningless, but what really matters is how many there are. So how many are there? There is, and also let's do another example. Let's say you have A and B. If we permute this, the only way is A and B, which is 1 itself, and then B and A. So it looks like there's some correlation between this and then like the length of this and how many permutations you have. So really the number of permutations is 3 or n factorial, n being the length. So 3 times 2 times 1 is equal to 6. And we have 6 of them in here. And when n is 2, it's going to be 2 times 1, which is just 2. If you have 4, that's 24. I'm not going to do all 24, but that's the whole idea. There's n factorial ways to do that. So insertion of a single node into a binary tree with n nodes. So the average case is going to be log of n, because most of the time, and it's not saying it's skewed left or right, but we're just going to assume on average it's going to be log of n. On average, your tree is probably not like trash. It's not like, like all on one side, like just skewed completely on one side. Hopefully, it's like at least something like this, maybe. So you're just on average, it's going to be like that as you insert values. You're not going to always insert the worst possible value you can, but assuming you do, your worst case is going to be O of n, because let's say you want to keep inserting. You insert this value, okay, 1. You go through 1 element. Then you insert this value, you're going to go through 2 elements, then 3, then 4. So notice how as you insert, every insertion operation is going to be growing linearly as you end up adding a value. And the next one would be like this, and so on. So that's the whole idea with that. Then number 4, deletion of a single node in AVL. Everything on AVL is log of n, since it's all height balance and everything. So it's just log of n, everything on AVL, everything on heaps as well. And merging a sorted array of size P with another sorted array of size Q, producing a newly allocated sorted array of P plus Q elements. Okay, so you guys have done this in merge sort a bunch of times. So let's just run through it and see like how it will work. So let's say we have an array. I'll do a perfect power of 2 so you guys can see it. So the way merge sort works, okay, so you end up stopping at the base cases, so there's just one element. And then what you end up doing, you end up merging this half with this half to create this like sorted like sub array in the in the overall array. So then this section, once you merge it, is going to be sorted properly. Just this section right here. So you can think of this as your P, this is your Q, or this is your Q and this is your P. It doesn't matter how you look at it, it's still the same. So of course, right here, we know that they're always going to be the same when it's a perfect power of 2. But let's say you didn't have a perfect power of 2. Say you had something like a little different, but let's just do 7. Okay, so we would end up going from, remember the whole thing with something like merge sort is kind of, you're going to take low plus high divided by 2, and this is our mid. So m is equal to 0 plus 6, which is 6, divided by 2, which is 3. So m is 3. And what we end up doing is we're going to end up merging, after we recurse down and we come back up, we're going to end up merging everything in red with everything in blue. Okay, that's not blue. Everything in blue. So now in this case, P and Q are not necessarily the same value. Now, if we take this a little further, once we end up recursing on this half, then we're going to have a perfect power of 2, because notice how we have 4 elements. So right here, then that's where we're going to go. We're going to be back at perfect powers of 2, and so on. But my whole point is that P and Q, when you're merging, are not always going to be the same. So it's not safe to just say, oh yeah, it's merge sort, power of 2, it's probably the same thing. No, you can't go by that, because it's not always the same. So right here we have P equals 3, and then, Q equals 3, and we have P equals 4. So really, whenever you do merging, you're going to have to end up comparing this element against this one at the start, and whichever one you end up choosing, let's say we end up saying this one is smaller, then now we're going to compare this one against this one, and then we're going to end up doing the same thing But the whole idea is you're going to end up going through both lists. So by ending up of going through both lists once, so we're going to end up stopping here. And then right here, we're going to end up going through this list until the end. We end up going in total, even though we're comparing at every step, we end up in total going P plus Q total things. So, okay, that's perfect timing, but it's P plus Q in any case, because you're never going to process P twice or P squared or Q squared or anything like that if it's only one sorted array and another sorted array. So yeah, O of P plus Q. So that's the answer for that right there. And let me see. Printing out each permutation. Why did they get n times n? Oh, okay. So this, I can explain why I put n factorial, not n. So they said printing out. So they're just counting printing out as an O of n operation, which it makes sense, but typically when they ask for a runtime of permutation, they just say it's just n factorial. But since they want you to print every permutation, since there's n factorial permutation, it's going to take n time to print every single one, because there's n letters. So that's where they get that n multiplication of n factorial. So yeah, watch out for some small things like that. Like I just saw permutation, I went straight through to n factorial explaining it, but they'll try to get you with little things like that. So yeah, there we go. And let's go on to the next question. So since it's getting late, I'm just going through them. You guys can work on it alongside me, or just watch. But I recommend you guys to at least try while I'm doing it. So matrix factorization algorithm runs on inputs matrix of n squared, or n times n, runs in n to the 3 if the algorithm takes 54 seconds. Okay, so these type of questions, I was told they're not going to be on the foundation exam anymore, like these n times n matrix, because there was like an issue with students not really understanding, because this wasn't really taught in teachers' classes. Like this is one of those things that they ended up removing. So yeah, it's 2015. So let's just end up going down to this one. I believe this one is one that could easily be done, or with like the knowledge that we have now and what they're going to test us on. Okay, so let's go to it. So we have a string algorithm with inputs of length n and m, running O of n squared m time. If the algorithm takes 2 seconds to run an input of n equals 1,000, m equals 500, how long will it take to execute n equals 250 and m equals 1,000? Okay. So T of n equals C times n squared m. And we know that for n equals 1,000, m equals 500, we run 2 sec. Okay, so say okay, so we can just plug these values in. So you can say T of n equals 1,000, 500, but I'm just going to end up plugging in the actual runtime. So 2 equals C times n squared. So n is 1,000 times m, which is 500. And now this is where people waste time on the exam, honestly. So people are going to try and, do all this out and like try to calculate, okay, so this is like 50 million and whatever. The easiest way is to put this in powers of 10. You can break everything up into power of 10, move the numbers around. It might seem a little hard if you're not too good with exponents, but trust me, it's very simple. So I'll show you what I mean by that. So 2 equals C times, and what I'm going to do here is we can rewrite this value. So 1000 is really 10 to the 3. So 10 times 10 is 100. 100 times 10 is 1000. So I'm going to rewrite this. So now we have 10 to the 3 times, squared, times, and then now we have 500. So if we think about it, 500 is really 5 times 100. And 5 times 100 is equal to 5 times 10 to the 2. This is the same exact way of writing, or a different way of writing the same exact thing. So we can think of this as 10 to the 2 times 5. Okay, so now let's keep going. Remember the whole exponent rule. Exponent raised to another exponent, just multiply them. So 10 to the 6 times 10 to the 2 times 5. 2 equals c times 10 to the 8 times 5. And now we can just end up dividing all of this. So we end up with c equals, actually we write it on the same side, c equals 2 over 10 to the 8 times 5. Okay. So now we can go on to the rest. So now we're going to try to find the time for n equals 250, m equals 100. Let's see how long that takes. So now we know our constant. So then we're going to have, what was it? It was 2 over 10 to the 8 times 5. Now we multiply that by 250 squared times 1000. So again, we can do the same manipulation. So 250. I'm going to write this actually a little bit differently. So we can rewrite this as 25. So we write this as 25, and then let's think of this times 10 to the 1 times, and then we have 10 to the 3. So this is another way to rewrite what we have right here. And that's going to help us. If you notice, we have a denominator right here of a power of 10, and then we also have a 5. So that's going to help us, simplify stuff out. So let me just move this out the way. Let's move all of it out the way. Okay, so I'm going to have 2 times, then let's do 25. Okay, so 25 times 10 to the 1 times 10 to the 3 is 10 to the 4. And then now we have the denominator. So I'm just writing this in the easiest way to look at it. So 5 times 10 to the 8, right? And now from here, we can just simplify. So we can subtract these since we're dividing. So we're going to end up with 2 times 25 over 5 times 10 to the 4. And now from here, we can divide these out. So 25 over 5 is just 5. So we're going to end up with 2 times 5 over 10 to the 4. And again, 2 times 5 is just going to be 10. So 10 to the 1 over 10 to the 4. Subtract these out. 1 over 10 to the 3. So we have, so there's going to be 1 divided by 1,000. So that's a way to think about it. So this should be the final answer. Let's just make sure that we didn't mess up anywhere. Because one thing when it comes to these powers of 10, it might be easy to mess up, but this is personally how I always do it. So yeah, it looks like everything should check out. Let me just make sure. Because something fell off. Ah, okay, I see it. Okay, I'm gonna have to go back through this real quick. It will just be a simple fix. Okay, so what I ended up doing right here is when I have broken down this term, so this is 25 times 10, right? So 25 times 10, that's just 250 and then 250 squared. So this whole thing squared. So this is what I had mentioned. When you end up doing this, it's very easy once you get in powers of 10. But like I said, it's easy to forget something if you're not careful. So I wasn't careful, but I caught myself and time's not up. So let's end up fixing what we had. So we're gonna have 25 squared times 10 squared times 10 to the 3. So now we're set. So now we have everything correct. So let's just keep going with this. 25 squared times 10 to the 6, or sorry, 10 to the 5. Now let's plug this back in. Okay, time ran out, but let's keep going. To the 5, 10. Okay, so now we're going to subtract this out. Over 5 times 10 to the 3. And now from here, we can solve for 25 squared. So this is just 625. So we have 625 times 2 times 5. Okay, so 625 is actually 5 to the 4. If we divide that by 5 to the 1 right here, this is 5 to the 3. So we're going to end up with 5 to the 3. That's 125 up top. So 2 times 125 over 10 to the 3. So this is just 250 over 1,000. That's 1/4. So this should be the proper final answer. Yeah, there we go. So they ended up with the same thing right here. So this is one thing that I noticed from the way they do it. They always put it in powers of 10 if they can. And that's how they end up transforming things to make it easier to handle. But like I said, and like you just saw, you have to be very careful when you do that because it can make the whole process easy. But if you mess up, you can really mess up, just like I did. So you can see how I caught myself, how I realized oh, there's something off here. It was all at this step right here where I turned 250 squared into 25 times 10, but I had forgot to square that part. And when you end up doing that, you have to, square it to keep it consistent and then, transfer the square to both things. But I hope you guys see how it can make it easier. Like I said, just be careful. You should be good. Okay, so there's another one with the grid stuff. Just keep going past this one. Summer 2015. We're not going to be asked this. Okay, so let's do this one. This is probably like one of the most confusing questions you guys have probably will have on any foundation. So if you get this one wrong, just don't just don't beat yourself up over it because this is one of those questions that people end up struggling with a lot. So yeah. So it says the list is empty. So we want to consider the following function that takes a list of unique integers for input. And the list is empty, return 0. Choose a random integer from the list. Place every value from the list that is less than the value in list 1. Oh my God, this question is so poorly written. Place every value from the list less than the value x in list 1, every value greater than x in list 2. So they forgot like to write and here. So yeah, I don't know who wrote this, but so the whole idea, you pick a random integer from a list. You place everything that is less than it to the left and everything that is greater than that value, that random number you chose, to the right of it. So I hope you guys can pick up something from that. And like they said at the very bottom, what's the best case runtime and worst case? What standard algorithm taught in CS1 is this algorithm closest to? So there's an algorithm that is exactly like what this is right here. Yeah, let's just keep running through it so we can see what the answer is. So run this function on list 1 and store the result in the variable left answer. Same thing on list 2, store it on right answer. Add to the answer the function run on list 2, return the value left answer plus right answer plus x. Okay, so it's okay if you don't understand it. What really matters is not what they're returning, it's what's happening, okay? Because think about it, whenever you're trying to analyze runtime of something, like worst case and best case runtime or any runtime at all, you're not really thinking about the numbers that you're returning necessarily in this case, because really we're taking a list. So let's say a list of numbers. So let's say we have 6, 3, 2, 4, 9. And let's pick a random value. Let's say 2. Okay, so what sort of algorithm, you guys can like comment it if you pick up on it, but what algorithm would end up having something like this? Let's say, for example, this is a bad example. Let me pick a different number. Let me pick 4. Let's pick 4. 4 is a better number. What sort of algorithm would have something like, so remember, we selected 4. Everything to the left of it is, yeah, it's quicksort. It's quicksort. So quicksort's the algorithm. Everything to the left and everything to the right follows the same pattern. And you're going to end up doing that for 3, everything to the right of 3, everything to the left of 3, and so on. So this is quicksort. More specifically, line 3 is actually the partition algorithm as a part of quicksort. And that's what like you pivot and partition about like the whatever number you choose. So, and typically they end up choosing a random number because the whole idea is you have a big array of values. So remember, n, it's not going to be infinity, but n is supposed to be infinitely large. It can be 1,000,000, it can be 10, it can be 40. So you're trying to think average like as you grow. So the worst case for quicksort, we know it's n log n. So, or sorry, the best case and average case is n log n. The worst case is n squared. So n squared, that happens specifically when you have an array that is in opposite sorted order. So if you have something like this, think about it. Let's say you always pick from the right side for whatever reason. You're going to want to figure out how many values belong to the left of it, how many belong to the right of it. So really, let's say you place this right here. Everything is going to have to go to the right of this. So we're going to end up with 5. Then you're going to have, let's just say, it's not going to end up looking like this in the code. Let's say you have something like this. Then if you end up always picking the rightmost element, then that means you're going to have to do the same process on most of the elements left. And this is not actually, it's actually not going to move anywhere. So you're going to have to end up doing the same process right here. So you're just moving n values for every n like iterations pretty much for every n value. So now this is going to end up being 6. Then you have 9, 8, 7. You're going to have to end up moving all these values over just to place this one here, and so on. So this actually might remind you kind of an algorithm. It's like kind of like insertion. So this is the worst case. That's why they have like the worst case. It essentially kind of looks like insertion if it's in reverse sorted order. So that's like the whole thing with that. So that's why the worst case is n squared. And they're asking you to provide proof of the runtime. And in doing so, you may use results about known algorithms. So without proving the results. So like I said, if it's in reverse sorted order, that would be the worst case because, essentially you're going to have to move everything over to get the pivot into the right location, or everything in the right location in relation to the pivot. So everything is going to be shifted to the right to accommodate where something should be, etc. As for the average case, that's not going to end up happening. So, and we know that n log n is going to be the average and best case for quicksort. So pretty much you can just say what you know from CS1, like those little things, and that'll end up getting you the points. But really, it's just recognition of the algorithm, the worst case, best case, and what you already know of it. And in terms of what the return value represents, let's see, what is this value exactly? Store the results in a variable 1. Okay. So what exactly are they doing here? So you have unique integers. So there's no duplicates. Place every value in the list less than x and every value to the right, like greater than x. Run this function and store the results. So the problem with this question is they don't even tell you what it is you're storing. Like they don't mention, okay, left answer is going to be, this is from 2020 actually. They don't even mention like what exactly it is you're calculating with left answer or right answer. So honestly, I've done this question before, and I'm not gonna lie, at this point, I still don't know what they're asking. I always like understand it when I read it, but if you're in the exam and you see this, there's no way you're gonna know. So honestly, I don't know who wrote this question, but it's so poorly worded that they don't even really explain what exactly the value left answer or right answer is gonna be. Aside from this right here, left answer, right answer plus x, which in that case, then you can just say x is just the sum of all the values, because if you think about it, so you have to like read this here to understand what these values are, which is, it's kind of testing recursive thinking, but essentially x is going to be a random value. And the whole idea is you're going to end up pivoting once around every value for something like quicksort. So it's just going to be a sum of all the values, if that makes sense. So I know this question was very confusing, but we were able to get the majority of the points from it. And honestly, surprised if you got this part right here for what the answer actually returns. So recursively partitions a list into 2 pieces after removing 1 element, similar to how quicksort works. So notice they don't even mention removing an element. So you don't even see it anywhere. So n log n. The worst case runtime is n squared. And I explained why it's n squared. It will be similar to kind of insertion. Move n about n items every iteration for n times. Return value is simply the sum of all the values in the array. So yeah, in quicksort, you pivot around every value to be able to have the values in the proper location. So that's how you end up with that right there. Because remember, the whole idea with quicksort, you end up, your base case is going to be just like merge sort, where it's if low is less than high. So the smallest case where this breaks is actually going to be when, so for example, low is less than high. What invalidates this? So what invalidates this is if low is equal to high. So that's the smallest. And if low is greater than high, right? So if low is greater than high, let's say you have an array of size 2 and you have a low of like 2, so there's a 0, 1, and then your high is, for whatever reason, it's like 1, then you've kind of like exhausted everything you can search because low has crossed. So that means like initially you had like something like this to go through, but then somehow your low and high ended up crossing over. So your low, so your high is here, your low is here. So you've pretty much done as much as you can. This could happen, but it's not too typical. But the more important case is where low equals high. So the only case low equals high is if out of an entire array, you're going to be on one element at a time. And that's going to happen for n elements. So that's like the whole idea behind that. Because then you're going to end up recursing one way. You're going to say, oh, that's going to be 0. Recursing one way is going to be 0. And then you're going to have, so your left is going to be 0 plus x, which is the value they tell you here, plus what you get on the right, which is 0. So if you do this for all the items in the array, so this is just val at index. If you do that and you base case out at every single element, you're going to end up with the summation of all elements in the array. So that's just going to give you the sum of all elements. So I hope that makes sense. Okay, so let's do one more algo analysis. And actually, I want to get to one of the code ones. So I'll just end up doing this one real quick in front of you guys, and then we can go to the code ones and give you guys some time on that before we go over to base conversion and call it a night. Okay, so algorithm takes, or to process a query on an array of size n takes O of n squared time for n equals 10 to the 6. It runs in 125 milliseconds. How many seconds should the algorithm take to run for an input size of 64 million? Okay, so let's just go through it. So we're going to start off with 125 milliseconds. MS. And we're going to have C times square root of 10 to the 6. So what we can end up doing here, you can remember that a square root, let's say you have square root of n, this is just equal to n to the power of 1/2. So this is what a square root looks like in terms of like power. So you can write this as C times 10 to the 6 to the power of 1 over 2. And like I said before, the same rule you can do, multiply an exponent raised to an exponent. So 6 over 2 is just going to be 3. So C times 10 to the 3 is equal to 125. And that's we're gonna end up with C equals 125 over 1,000, or 10 to the 3. So I'll leave this here. So this is still in terms of millisecond. So we haven't like, bumped it up yet to seconds. Okay, so now let's go on. So we're gonna have T of n equals 64 million. So they gave us 10 to the 6, and 10 to the 6, by the way, is just 1 million. And you can get that by just doing 1, 2, 3, 4, 5, 6. And that'll give you, your 1 million. Just have 6 zeros. And we have this times 64. So what I'm going to end up doing is just rewriting this 64 times 10 to the 6. this is equal to 125 over 10 to the 3 times, and now at this point, let's see, we're plugging in n squared, and n is just going to be 64 times 10 to the 6. And this you guys are going to see why it's helpful to put things in terms of 10, powers of 10, like I did before. This one's going to be a lot simpler to see, so it's not going to be as tricky, but let me just break it down. So, quick example. I'm just going to take a sub-example of this to explain something. So, if you have square root of 64, this is equivalent. So I know this is just 8. This is equivalent to 8. But another way you can look at this is also equal to square root of 8 times square root of 8. Okay, so, and let's just see why real quick. You can multiply it, but the whole idea is this is 8 to the power of 1/2 times 8 to the power of 1/2. Remember what happens when you have the same base. B to the x times b to the y equals b to the x plus y, or to the power of x plus y. So that means this is just going to end up being 8 of 2 over 2, which is just 1. So what you can end up doing is breaking up the square root into, literal segments. So what I mean by that is you can just break it up into 2 multiplications. So you can set this up as square root of 64 times square root of 10 to the 6, and it's the same thing as this right here. So I hope that makes sense. And now, as you remember, we have to put this here into the 3, so this is our constant. And now from this point, we can just take the same answer that we put up here. So 10 to the 6 over 10 to the power of 6 to the power of 1/2 is just going to be 10 to the 3. So now we're going to have 125 over 10 to the 3 times 8 squared, 64 square root is going to be 8 times, and then this is going to be 10 to the 3. So this is what we're dealing with. So notice we have a 10 to the power of 3 in the denominator and in the numerator. So we can just remove this element right here. You can set, and now we're going to end up with 125 times 8 over 1. And this is just going to be, actually, this is going to be, I believe, 1,000. Let's just confirm. Yeah, 1,000. So 25 times 8, that's just 200. And it's going to be 800. So 1,000. We end up with 1,000. And remember, we had this in terms of millisecond. So we have to get it in terms of seconds. So millisecond is like scaled down from seconds. So you just got to multiply it by 1,000. Yeah, so there we go. So you just divide it by 1,000 and then 1. So right there. And 1, there you go. So that was it. So there we go. They ended up doing the same exact strategy as well. So it definitely helps to break this up and keep it in powers of 10. So anyone have any question? Okay, so let's go on to the last section, which is base conversion. And this is going to be the last thing we're going to do. Okay, so I'm going to go ahead and give you guys time on this one so you guys can try it out, since I haven't given you guys time to do them. So there's only a couple on base conversion. There's not really many. And yeah, they tend to be on the older side. So it's only a couple you're going to have to do, but it's still applicable. So yeah, I'll be back in 2 minutes. So I'm probably gonna end up doing one next week, but I don't really know what I do. Like, what did you guys want to see next week? Because in terms of topics, I'm pretty much done with this. Once we're done with base conversion, then every topic has been covered. So yeah, just tell me what type of topics you guys will want to see. I'm probably gonna end up doing something next week. I always do something the week of, so I did that for night hack. Okay, yeah, I can definitely go into summations and curses as well. Tries to. Yeah, bitwise. I already did bitwise on the last session. I don't know if you were there, but everyone, look, it's just gonna be a session where anyone can come in and ask me a question very relating to whatever topic they want. That's probably gonna end up doing. I'm sure there's gonna be a lot of people, so I'll probably just do like, one or two questions per person, like whatever people are the most weak on. Yeah, and like I said, for the URL for the whole for my sessions that I've hosted, just go to this website. So let me move this far out the way real quick. So the website is Pass the Foundation Exam.versal.app. And right here, you're always gonna have it right there. So you can just click on it and you'll end up seeing it right here. So I did 3 of them, and then I also did one specifically on like answering some of the bitwise operator questions. So yeah. Are all these topics guaranteed to be on the exam? So what do you mean guaranteed? Like they're all going to show up, or like they can pick and choose from? Yeah, it changes every year. So for example, one thing that I noticed is they're pretty much actually Guha told me this because I had Guha for CS1 in the fall, and he had said that for the January exam, which was the bitwise question of painting the fence, that one is like a bitwise question. Then the next one, I think the last one you guys did was a base conversion in the last exam. I'm not sure what that was for. I think it was a bitwise question. It was bitwise. Oh, okay, yeah. So yeah, I wouldn't be surprised if they pull out a base conversion, honestly, but it could be bitwise too. So you gotta cover all your bases. Yeah, I'll just give another minute since I'm just talking. Okay, so let's get into this question. So convert 160.1654 base 8 to hexadecimal. So this is in base 8, and we're going to go to something in base 16. So hexadecimal is 16, so just remember that. We're going to something in base 16. So the easy way to do this, when you're in base 8, let's just think of this instead of 8 as 2 to the 3. And what we care about is the 3, right? And they want us to end up going to base 16, so hexadecimal. And we can think of this as 2 to the power of 4. Highlight on the 4. So one way, or the easiest way to end up doing this is, since we're going from powers of 2, since this value, let's say this is a k, and this is also like k, what you want to end up doing is taking this 164, and for every single value, so every value right here, this value right here, this value right here, and then this value right here, we're going to want to write what it would look like in terms of 3 bits. So what I mean by that, in terms of bits, 1 right here would, okay, not the ruler, 1 would look like the following. So it would look like 001. Okay, so this is what I mean when I say write it in terms of bits, but the number of bits you're going to use for this right here is going to be whatever this k value is. Okay, so this is what it's going to look like in octal. So we're going to do the same thing for 6. So 6 is 0, 1, 1. 5 is 1, 0, 1. And then 4 is 0, 0, 1. Okay, so that's what it looks like in, we took it from octal, so this value in octal. And this right here, this whole entire expression is going to be base 2. Okay, so this is what it is in binary. So now from here, we're going to end up doing is taking this expression in base 2, and now we're just going to group all of these values in groups of 4. Since we're trying to go from octal, which is 2 to the 3, to hexadecimal, which is 2 to the 4, we converted this number from octal to binary, and now we're just going to group them into groups of 4. And so the way we know that we can easily do that is we have 3 groups of 4, 12, and yeah, there's a 4 in here. So now that means we're going to end up having 3 groups of 4 as opposed to 4 groups of 3. So what I mean by grouping is you're just going to start from the right side and then just group in 4s. So like this. And that's just going to be your final answer. So in hexadecimal, it would just be 0, 0, 1, 1. Then you're going to have 0, 1, 1. I'm sorry, 0, 1, 0, 1. And now the final values is going to be 1, 1, 0, 0. So now from this point, we have to go down to hexadecimal. So now we grouped it in terms of 4. So now we can go into hexadecimal. So this is still base 2 again. And now I have to do it in hexadecimal. So the way hexadecimal works is you have values from 0 to 15 inclusive. So you can have 0 to 15, but there's one thing. Once you hit 9, so 0 to 9, after 9, it's going to start at A, B, C, D, E, F. And this is just representative of 10, 11, 12, 13, 14, and then 15. So now we're going to end up doing is just taking these red values and saying, okay, what letter is this in, like what index would this be in hexadecimal? So we're just going to take these groups of 4. So actually, let's start from this right here. So we have 0, 0, 1, 1. So that's going to be 2 to the power of 2 plus 2 to the power of 3. So that's going to be, okay, I didn't mean for that to show. So this is going to be 8 plus 4. So there's just 12. And 12 is just going to be C. And this right here, we're going to have, this is 2, and this is 8. So this is just 10. 10 again is A. And this is just 0, and this is, this is 1, and then this is 2. So that's going to be 3, and 3 is just going to be 3. So this is going to be our final answer in hexadecimal. So again, to highlight the whole process, we went from, we took note of, what K it is in terms of power of 2. We put them into groups of K size, so groups of 3 into binary. After we did that, we grouped it in terms of 4, which is what hexadecimal is. It's 2 to the 4 maximum. Because notice there's 4 slots, so the biggest value is just going to be this right here, a 1 all the way to the left, which this is just equal to 16 in base 10. So that's the whole idea. You group it into, what 16 can fit into, and then from there you just, translate. So that's how you convert that. Okay, and as for the other question, I'm gonna try to see if you can just, so 120, 1925 base 10 to octal. So let's just still do it, even though kind of peeked at it, but 1925 and base 10 to octal. Okay, so octal is base 8. So really we're just looking 1925 base 10 to something in base 8. So what we're going to end up doing is you just have to divide the number by 8 and then take, like, if there's a remainder, just store the remainder, and that'll end up giving you the value. So whenever you went from base 10 to another base, you just divide by whatever that base is you're going to go to. So we can start off with 1925. We can divide by 8. And of course, it's going to be harder to do just looking at it, but we can do this method right here. So 8 doesn't go into 1. So I'm just going to write nothing here. Then 8 goes into 19 twice. 13, bring this down. 8 goes into 132 how many times? So let's see, so we can do, let's see, 8 times 14. Oh, I'm gonna do like this. 14 times 8. Yeah, so we still have some room to go. We can add another 8 and another 8. So that'll give us 128. So at most we can go 16. Oh, actually, I messed up. I brought down this 1 by accident. It goes in 4 times, my bad. Okay, and then now we have a 5. So now right here, 8 goes into 5 0 times. So we just have 5. And now we're going to store this remainder. So we're going to store 5, because this is what's going to end up building our answer. So now we're going to end up doing, we're going to take this value and keep dividing it by 8 until eventually we get to 0. So 240 divided by 8. So let's just do it quickly. It doesn't go into 2. So now we're going to have 24 goes in 3 times. And yeah, so we're going to have 0, bring down the 0, 0. And 8 goes into 0, 0 times. So now we're going to have 30. So now we're keeping track of these remainders again. Now we're going to do the same thing. 30 divided by 8. We know this is just going to be 3. So 24 going to be 6. So we just have a remainder of 6. There's nothing to bring down. So far we have a remainder of 5, 0, 6. And we have 3 left. 3 is not 0. So 3, 8. How many times does 8 go into 3? It goes in 0 times. So now at this point, this is where we stop. And whenever you have something where it just goes in 0 times, this itself is going to be your remainder. The whole idea is just kind of like mod. It's kind of like something like this in a way. Like it just doesn't go in, so you just stay with that value. So that would be your remainder right here. So really the final answer you're going to have in octal is just going to be going upwards. So go upwards, and then that's going to be the answer. When I say upwards, I mean go from the last remainder you had to the very first, but you're just adding those numbers in sequence. So 3 right here, then 6, then 0, then 5, and then this is just going to be in base 8. So this is going to be our final answer. So that's the whole idea of how you can do it. It's just division, pretty much. So let's see if we got it right. So 3AC, they ended up with 3AA. I think that's just a typo right there, because they have 3AC here. Yeah, it's definitely 3AC, because this is 10, and actually, hold on. This is 8 plus 4. This is 12. Yeah, and we checked right here that 12 is C. So this 3AA, they just wrote it wrong, and they meant 3AC. And then right here, 3, 6, 5, base 8. So that's that. Let's go on to the next question. Okay, this question, if you see it whenever you're using this website, just skip it. They'll never ask you this. This question was like probably one of the hardest ones on any of the exams. So they're not going to make you code anything base conversion. There's a reason this is in 2015 and they've never done this again. So let's go on to the next question. I'll just give you guys a couple minutes, 2 minutes, and yeah, after this, there's only one more question, so we can do it quickly. There's really only like 4 or 5 bitwise questions across all the exams. There's not really that many questions to go off of, but they're not as bad as they. Okay, convert hexadecimal number AF to E9 to binary without first converting to base 10 equivalent. So we have hexadecimal AF2 E9, and that's going to be hexadecimal, so base 16. And pretty much we're just going to follow the same pattern that we did before, where, remember how for the previous question, I actually have it up here. So to get it into, final hexadecimal format, we just went from binary. We just like calculated what the binary would be for this specific value. So right now, instead of going from here to here, we're actually just going from here to here. So that's easy. You just say, okay, 3, what is that in binary in like a group of 4 bits? Okay, what about A? What is that in binary in group of 4 bits, etc. So that's all you got to do. Is just reverse the process pretty much. So let's say A, remember it goes 0 to 9. And then we have A through F. Let me just write those out real quick. $15. Okay. So A is going to be 10, and 10 is just this right here. Then we have F. That's going to be 15. So one rule or one trick you can do whenever you have a perfect power of 2, so for example 2 to the 4, any perfect power of 2 is just going to be a single bit on. So that would just look like this right here. So this is 16. This is a perfect power of what a perfect power of 2 looks like. It doesn't matter what it is. If it's like 2 to the 8, it's just going to be 1 and then a bunch of zeros to the left and then 7 zeros to the right. So there's only going to be 1 bit on. How is that 10 in binary? My A. Oh, my bad. So this is 2 and then this is 8. There we go. Okay, so now we're gonna do F. So what I was saying was when you have perfect power of 2, you're just gonna have one bit on. Any perfect power of 2, so if you ever do just like this, remember from recurrence and summations, 2 to the k minus 1, it'll always just look like, of course, to the left, a bunch of zeros, but then you're gonna have to the right, it's just gonna be a bunch of ones. So that's just a trick. Whenever you see something that's like a power of 2 minus 1, it's just all gonna have all the bits on. So yeah, just so you guys know. So 15 is just gonna be is right here. Now we're gonna have 2. 2 is just gonna be 2. E is going to be, let me do just 9. So E is 14. So that's going to end up being, let me see. So it'll be 0. So it's going to be 8 plus 4 plus 2. There we go. And now we're going to have 9. So 9 is just going to be this right here. So this is 8. This is 1. That's 9. And that's pretty much it. That's our answer. That's all you got to do. So this right here is your answer. Now let's do the second one. Let me see how much time. We have 2 minutes. We could probably get the second one done. So yeah, I don't know where they got this picture from, but yeah, so Frank is a team lead software testing at his company. He's celebrating his birthday. Some of his coworkers baked the cake and thought it would be really cool to put candles representing his age in binary. The unlit candle represents 0-bit. From the picture, how old is he? So we have the first 3 bits are on. The 2 bits to the left of them are off. And this bit right here is on. So this is equal to 7. And we have 0, 1, 2, 3, 4, 5. So 2 to the 5 plus 7 equals 39. So there we go. That's the answer. Yeah, 39. Is it a cake or a hat? Yeah, I don't know, honestly. It does look like a hat, though, I'm not gonna lie. But yeah, so this is the right answer. 10, 10, 1, 1, 1, 1. This, that, and this. Okay, so now I think we have one last question left. Yep. So let's just hop straight into it. And then we can call it night. Unless anyone has a question real quick, and then I'll help you out. So we're going from FAD 8 to 16. So we kind of just did this type of question not that long ago. We did one that was very similar. So first things first, you convert it to binary since you're going from base 16. So in our previous question, what we had done was we went from, I think it was from 8 to 16, and now we're just going from 16 to 8. So you just pretty much have to reverse what you ended up doing. Something in octal. So let's get this in binary. So let's just do this quickly. So this F is 1, 1, 1, 1. A is 10. So that's 1, 0, 1, 0. D is 13. It's going to be 1, 1, 0, 1. And 8 is going to be 1, 0, 0, 0. Okay, so there we go. We convert it to binary. And now pretty much what we end up doing is we just group them up into, like I said, groups of 3. So we have 4, 4, 4, 4. So we have 16. Let's put it into little groups of 3. Start from the right side. So what we'll end up doing is, and by the way, I just wanted to mention something. Whenever you're gonna see that 16. So we have a total of 4 groups with 4 bits each. That's 16, and we know that 16 is not divisible by 3. This is not the case. You cannot divide 16 by 3. So what you end up doing is you just end up adding to compensate for like it not being divisible by 3. You just add a couple of bits on the side. So when we think about it, multiples of 3, we have 3 times 5, which is 15, right? But we need extra bits, so we're just going to kick it up to 3 to the 6, 18. So if we have 16 here, we just have to add, from the next multiple of 3, subtract how many bits you have right now. So we're just going to add in 2 zeros. So now what's going to end up happening, we're just going to group these into 3. So now it's going to look like 0, 0, 0, 0. Okay, and now from here, 1, 1, 0. So we just did this, we just did this. I'm going to do it again. So start 1, 1, 0, 1, 0, 1. These 3, so 1, 1, 1, and 0, 0, 1. And that's pretty much it for converting to, or like grouping it in terms of like octal. So now what you're gonna have to do is just translate this into their number representative in binary and like combine them. So pretty much what I mean by that, this is 0. This right here is 3. This is 3. This right here is 5. This is 7. And this is 1. So this is your number in octal. 1, 7, 5, 3, 3, 0, base 8. Okay, and now what we're going to do is the next question. So 210, base 10, 2 hex. Okay, so we kind of just did this one, but let's just finish it out. So divide this by 16. Doesn't go into 2 at all. So we're just going to do 1. Get 5, 52. It goes in 3 times. So that's 48. Then we get 4. And that goes in 2 times, which is 32, 8. So we have a remainder of 8. And this is non-zero. So what's going to end up happening, we're going to do the same thing. Do 132. So it doesn't go into 1. So let's just, it doesn't go into 13 either. And we're going to just have to see if it goes into 132 right off the bat. So let's see. I think the best we can do is probably, it's probably 8. So that's going to be 128. So 4, 128. Yep. So you can go in 8 times at least. And we're going to have a remainder of 4. And now at this point, we're just going to have to do this one last time because now we know that we have 8 and 16. 16 does not go into 8, so this is part of our remainder. And now we're just going to take all these remainders going back up, and that will give us our final answer. So we're going to have 8, 4, 8, base 8, and that is the final answer. Or sorry, base 16, base 16. We just went to base 16. Here we go. So 8, 4, 8, 16. And this is 1753308, base 8. So let's see. Okay, so I haven't selected the answer. Done. Well, let me see what everyone said. So how would you convert from hexadecimal back into decimal? Oh, for that, let me see. I think you just put it in terms of the powers again. Let me see something. So if I do, let me just use a calculator real quick. In 1 second. Okay, 1 second. I think I figured it out because I haven't done this in a long time, going backwards, but I think it's pretty easy. 16 times. Yeah, okay. So this is how you do it. So any base into, when you're going to base 10, all you got to do is the following. So it's the same process you kind of do for a binary, but instead of base 2, you do base 16 right here in this case. So what it would look like is you do 8 times 16 to the 0 plus you do 4 times 16 to the 1 plus 8 times 16 to the 2. And this right here is going to give you 2048. This is going to give you 64. And this right here is going to give you 8. 64 plus 8 is 72. And these two numbers right here end up adding up to 2120. So that's how you end up with that in base 10. Okay, so anyone have any last minute questions before I stop? Like the next time I end up doing a session is going to be next week, and going to be a lot of people probably. So yeah, just let me know if anyone has any question or anything. Oh yeah, permutation and flood fill. Okay, so permutations is kind of weird because, like I said, I took CS1 with Guhai in the fall of last year, and back then we still went through backtracking. And we also cover permutation. I'm not sure how CS1 has been. So for anyone who's taken CS1 lately, I know someone who did take CS1 lately, and they did do permutation, but they didn't do backtracking. The only thing with permutation is even though they don't tell you, it's actually uses backtracking. So that's like the only thing. For example, when different teachers do it different ways, but the way Guha taught it to us is like you have a used array and used of I, you turn on to 1, then you end up recursing. When you come back from the recursion, you set used of I to 0. So that means like you can now use that value. Another example would be Ahmed. I know Ahmed, the way he does it is he ends up like swapping whatever values at an index with another, and then he recurses, and he ends up coming back from the recursion, and he swaps it back. So those are both permutation. They're both use backtracking, and yeah, they can still be on the test, but I would just make sure you understand permutation. I will say that's one of those topics that's much harder to like understand. Like especially if you haven't taken discrete, and taking discrete definitely helps. You don't have to take it. Like I figured it out without that, but it's one of those things that you have to understand and really be good at following the recursion. I think it's still worth it to go through it and learn it because learning and how permutation works, being able to trace that code with how complex and all the stuff changing, I think that'll really help you with recursion. So I would still do it. As for what is it? Back for flood fill, I would expect it to be on the exam. Now I'm not saying it's going to be on this one or anyone in the near future. It's just something that can come up. It's something everyone was probably taught. So yeah, I would still know how to use flood fill. Flood fill, I've already went over in another question actually when I did what was it? Recursive coding. It was actually if you go to this link right here, let me go to right now.